In the next section, we're going to see applications of integers, and we're specifically going to talk about a form called scientific notation. So we're going to first kind of make the distinction between what we normally write and what the scientific notation is. Then we're going to talk about how to convert back and forth from one to the other. And then finally, how do we combat operations involving this? So how do I multiply numbers in scientific notation? How do we divide numbers? That kind of stuff. So the very first thing we want to go through is we want to talk about what is scientific notation. And really, this is just a beneficial form when we have a really large number or a really small number. So if you think of like the distance to the moon, if I had to write that out in miles, it would be awful and it would take up so much space on a page. So instead what we can do is use this notation because we know that these exponents are representing repeated multiplication. And really decimal points are just powers of 10. So every time you move a decimal, it's 1 power of 10. So scientific notation has a very specific form where it's some number times 10 to a power. But that number has to be something that starts with a 1 or some number between that and 9. So I'm not going to have 10 point something. I'm not going to have 0 point something. Your scientific notation is always going to start by a 1, a 2, a 3, 4, 5, 6, 7, 8, or 9, immediately followed by a decimal point. And then the remaining numbers that come after it are the rest of the significant ones. So this is what we have to have. The decimal has to be after that first non-zero number. Okay. So we're going to just look at a couple different examples and we want to figure out, is this number in appropriate scientific notation? So looking at our first one, we have 8.23 times 10 to the 7th. So here the value of A is 8.23, which is definitely bigger than 1 and less than 10. So yes, this number is in scientific notation. It's 8 immediately followed by the decimal. For the second one, we have 0.23. So the value of A here is really, we have 0.23. So my decimal comes after a 0, which is not what we want. It has to be 1, 2, 3, all the way up to 9, immediately followed by a decimal. So no, this one is not in scientific notation. If the decimal was after the 2 instead, then we would be good. And for the final example, which accidentally is labeled an A as well, so number C, we have 47 times 10 to the negative 4. And here the value of A is 47. So again, this one is not in scientific notation. That decimal would have to be in between the 4 and the 7. Okay. Now we want to get into how do I convert between what's known as our standard form to this scientific notation. So starting with whatever number you have and putting it with these 10 to powers in there. Very first thing you want to do is you want to start by putting a decimal point after the first non-zero number. Important that it's after the non-zero number. Then your decimal started in some point. You want to count the number of spaces it's going to move. Whatever this number is going to be your exponent. It's then a matter of, is it a positive exponent or is it a negative exponent? The way I really like to think of this is I like to think of it in terms of big numbers and small numbers. So if I have 10 to the 100th power, that is going to be a gigantic number. So anything with a positive exponent is indeed representing something that is a big number. If I have 10 to the negative 5, that's a really small decimal because it's 1 over 10 to the 5th. So anytime we have a negative exponent, it's representing a small number. Because I'm terrible at knowing whether I have to say left or right. My directional sense is atrocious. So I like to think of it in those terms instead. But if you personally like to think in terms of directions, if you're starting with a really big number and your decimal's here and it has to move to the left, your exponent is positive. If you're starting with a really small number and your decimal needs to move here, it's moving to the right, it's going to be a negative exponent instead. So we're going to just do a bunch of examples. We want to write the number that's given to us in scientific notation. And so again, very first thing, my decimal is currently sitting here. I want to move the decimal right after the 3. That is my first non-zero number. If we do that, it has to move 1, 2, 3, 4, 5, 6, 7, 8 places in total. Okay, so I know that's going to be the exponent on my 10. So what we do to write this in scientific notation, the decimal goes right after the 3. I copy down all the important numbers. You get to leave off all the extra zeros. Those don't make a difference. And now we're going to times this by 10 to a power. And in this case, because it is a large number, it is going to be a positive exponent. So in scientific notation, this is 3.22146 times 10 to the 8th. Okay. Let's try another one. Currently our decimal is here. I got to move it after the first non-zero number, which is a 1. So it has to move 1, 2, 3, 4 places. Okay. And this is also a large number, so my exponent is going to be positive. So I write all my numbers down until I hit the last important digit. You do have to include zeros that are trapped between things. But then we're going to times it by 10 to a power. And then again, it's going to be 4 because it is a large number, so positive 4. For the next one, we've got to do the opposite thing. So I have very small decimals here. So I need to move the decimal to right after the 5. And in doing so, that's going to have to move 1, 2, 3, 4, 5 places. So in scientific notation, our decimal's right after the 4. We copy all of the important numbers, and we're going to have 10 to the 5th. But because it is such a small number, our exponent is going to be negative instead. And then last but not least, first non-zero number is 1, so it's going to move right after that. And it's got to move 3 places this time. And again, because it's a small decimal, it's going to be a negative exponent. So I write my decimal after the 1. We times it by 10. 3 is in the exponent, and it's negative because it is a small number. Okay. Now if we're going to do the reverse, and we're going to start with the number in scientific form, and we want to convert it back to its original quantity, we're really going to have to do exactly the opposite as to what we did before. So this is also why I don't like memorizing left and right, because now I'm moving things in the opposite direction when I'm converting to the other form. So if you need to, the directions are right here. You're going to move decimal right when you have a positive power, left when you have a negative power. But really the way I like to think of it again, if you have a positive power, this is again going to be a big number. If you have a negative exponent, it is a small number. And that exponent is just telling you the amount of times you need to move the decimal. So for our first example, we have 10 to the 8th power. That is a positive exponent. It's going to be a big number. So what I'm going to do is I'm going to first start by copying all of our important numbers. And currently our decimal is sitting right here. But I need to move it 8 places, and I want it to be big, so I've got to move the decimal to the right. So there's 4, 5, 6, 7, 8. Our new decimal is going to go right here. Any of these blank spaces we have, we're just going to fill in with a placeholder of 0. So we're really adding 4 zeros at the end. And this doesn't look so nice, so we need some commas to really indicate what this is. So we've got 3, 3. So in standard notation, this is 501,420,000. Next one, we have a negative exponent, so that's going to indicate that this is a small number. I definitely don't want to move the decimal this way, so instead the decimal is going to go to the left. Because it's going to do that, I want to recopy these numbers over here because I know I'm going to need some space in the beginning. So currently our decimal's sitting right after the 8. Our exponent's -4. That means we need to move it 1, 2, 3, 4 spaces. Our new decimal is going to be right here. And all these blanks we're going to fill in with zeros. So this is 0.00018131. At least now we want to get some practice. Just how can I multiply these things? How can I divide them? Adding and subtracting, you're not going to do a ton of, because really you can only do that when they have the same exponent. So instead what we're going to do is we're going to work through 2 examples, and our first one is going to be multiplication. And the thing you need to remember, just like in our exponent and our exponent rules, the order you multiply stuff doesn't matter. So I can rearrange this however I want. So what I'm going to do instead, this is really just 3.4 times 10 to the 6 times 2 times 10 to the 4. We just use this symbol here because it makes it a little more clear that this is a specific notation. But all that does is it still represents multiplication. So instead what we're going to do is we're going to group together the 3.4 and the 2. And then the 10 to the 6 and the 10 to the 4th. Because we can rearrange multiplication. 1 times 2 times 3 times 4 is the same thing as if I flip this around to anything that I want. The multiplying still works exactly the same. Okay. So in doing so, the first 2 we can actually multiply. 3.4 times 2 leaves us with 6.8. And then our power of 10s we can use our exponent rules on. We go ahead and we just add those 2 together. So this leaves us with 6.8 times 10 to the 10th. And the key though in this is it does say to write our answer in scientific form. So if I go through and check this, the decimal is after the first non-zero number, so we are good. This is in scientific form. Okay. We're going to see in this next one, it's not going to work as well. Okay. But we still get to apply the same concept. So I'm doing this division with multiplication. We can go ahead and split these fractions. We'll put the 5.4 and the 9 together, and the 10 to the -3 and the 10 to the 9th -9 together as well, because we would just multiply these 2 fractions across. If you take 5.4 and divide it by 9, it gives you 0.6. And then using our exponent rules, we go ahead and subtract these 2. So this leaves us with 0.6. -3 minus -9 is really -3 plus 9. So it leaves us with 10 to the 6. And this is where we have a bit of a problem, because this decimal is not after the first non-zero number. So really I need to move this to make it so that it works. So what I want to do is I really want to move this decimal 1 place here. So you have a couple different ways you can go about this. Because it's not such a super high power, you could write this out in standard notation and then convert it back to scientific form. Or we can kind of just think about this more abstractly and figure out, what does moving this decimal do to my exponent? So I'm going to start by doing the abstract, and then I'll show you it works the same if I convert it. So I really want this decimal to move 1 space here. And so my power is currently 10 to the 6. So if I were to convert this, I would move my decimal 6 places and it would be something that's much larger. So this positive exponent is really telling me I would go ahead and move my decimal 6 times anyway. To put this in standard form, I've got to move this decimal once. So really, I've taken one of those positions that I need to move away. So it's reduced my power to the 5th. If it was 10 to the negative 6, it would have the opposite effect because the negative exponent would tell us to move the decimal this way, but I'm moving it opposite of the way I naturally want. Okay? So that's kind of the logical explanation of why that occurs. But what we can also do is move this one out completely instead. So 10 to the 6 tells us our decimal's currently here. We move it 1, 2, 3, 4, 5, 6 places. Fill in all these zeros. So 10 to the 6 is really 600,000, which we then would have to write in scientific form. So we've got to move the decimal 1, 2, 3, 4, 5 places to right here. And it would be 6 times 10 to the 5th. So this works when you have a small power, but if it doesn't, then you got to think of it abstractly. And again, just to refresh on how we did that, the positive exponent tells us we're automatically moving the decimal to the right. I'm already, or if I'm going to move it 1 to the right to put it in the form, I'm going to have to remove 1 from this exponent because I've done one of those positions. If instead we had 0.6 times 10 to the negative 6, I'd have to move the decimal to the right, but this exponent's telling me to move to the left. So really, I'd have to move my decimal 1 extra spot. It would be 6 times 10 to the negative 7th to account for the fact that I'd then have to do another position movement. Okay.